Okay, today we're going to talk about binomial probability. Let's start by talking about what a binomial setting is. Binomial setting arises when we perform several independent trials of the same chance process and record the number of times that a particular outcome occurs. And there are 4 conditions for a binomial setting, and we can give the acronym BENS for that. B in BEN stands for binary. Okay, I need 2 possibilities, something I call a success, something I call a failure. Again, you can define what your definition of both of those are. I represents independent. Trials must be independent. That is, knowing the result of one trial must not have any effect on the result of any other trial. N in BUNS represents number. We need a fixed number of trials. Okay, so I know I'm finding the possibility out of 5, out of 10, have a fixed number. And S in BENS represents success. On each trial, the probability of success must be the same. Again, acronym BENS. So consider tossing a coin n times. Each toss gives either heads or tails. Knowing the outcome of one toss does not change the probability of an outcome of any other toss. We define heads as a success, then P is the probability of a head, and is 0.5 on any toss, again, because we have half heads, half tails on a fair coin. Number of heads in n tosses is a binomial random variable, and the probability distribution of X is called a binomial distribution. So the count X of successes in a binomial setting is a binomial random variable, and the probability distribution of X is a binomial distribution with parameters n and p, where n is the number of trials of a chance process and p is the probability of success on any one. The possible values of X are the whole numbers from 0 to n. Note, when checking the binomial condition, be sure to check the BENS and make sure that you're being asked to count the number of successes in a certain number of trials. So let's look at an example. Each child of a particular pair of parents has probability of 0.25 of having type O blood. Genetics says that children receive genes from each of their parents independently. These parents have 5 children. The count X of children with type O blood is a binomial random variable with n equaling 5 trials and a probability of 0.25 of success. In this setting, a child with type O is considered a success. Any other blood type is a failure. So we're going to find what's the probability that X equals 2, or that we have 2 children with type O blood. So if we look out one possibility of the first 2 being a success, 2 type O children, then I have 3 non-type O children. Well, probability of type O is 0.25 for the first. Probability of success on the second one, type O is 0.25. Again, the next 3 are not type O, so that would be probability of 0.75. If we multiply that out, we get 0.026, or about 2.6%. But remember, I don't necessarily just have to have the first 2 children type O. Again, there's different possibilities. There's different orders that I could have them in. And how many total arrangements do I have? I actually have a total of 10. So we need to take that probability of 2.02 and multiply it times 10, because I actually have 10 options for 2 children with type O. So you multiply that by 10, you get 0.26, or about 26.37%. So we can generalize this into an equation, okay? If I want to find the probability that X equals a certain number of successes based on the trials, I can write that as the probability of success raised to the exponent how many successes I want, times the probability of failure, 1 minus P, raised to the number of failures. And how I can find the number of ways of arranging those, that's what's called a combination. And it can be found using this formula. I believe this is on your AP formula sheet. N over K, which gives us the formula n factorial, so your number of trials factorial. So if it's 5 children you're wanting, 5 times 4 times 3, so forth, divided by your number of sexes factorial times your number of failures factorial. But luckily the calculator can provide this for you as well. So on the calculator, you can hit menu probability combinations, and it's going to give you this little NCR. You're going to put your number of trials. If we're looking at our blood example, you would put 5, and 2, because we wanted 2 typo. So the binomial coefficient counts the number of different ways in which k successes can be arranged among n trials, and the binomial probability pk equals x equals k is this count multiplied by the probability of any one specific arrangement. So we can take that probability raised to number of successes times probability of failure raised to number of failures and multiply that by the number of combinations in k. Again, this formula is on your AP formula sheet, but luckily, calculator will also do the work for us as well. So AP test does allow you to use the calculator, and I will show you what work you need to show in order to use that. So calculator has this formula for a binomial distribution found through menu, probability, distributions, binomial, and we're going to do a binomial PDF if we're looking for the probability of something equaling a number. And we're going to look for binomial CDF if the probability is less than, equal to, greater than, equal to. And I'll show you examples of both of those. So let's look at an example. Again, if we go back to our blood type, find the probability that exactly 3 of the children have type O blood. So again, we need to define what's a success. Let X equal the number of children with type O. Failure is going to be anything without type O. So here we know that our number of trials is 5. Again, suppose the parents have 5 children, and probability of type O is 0.25. So we could use formula. If we use formula, again, we're going to have probability of type O 0.25 raised to a number of times we have, which is 3 times probability of failure 0.75 raised to how many failures we're going to have, 2, and multiply that by combinations of 10. But luckily, calculator does the work for us as long as I show the work. Okay, so for AP test, for the AP test, you have to show this step for the calc work. So if you're not going to write out the whole formula, we need to go to menu, probability, distributions, binomial. Okay, so your calculator work you must write down as you're showing work part is binomial. We want PDF because it says exactly 3. And how many trials do we have? We're going to do 5 children. So n equals 5, comma, probability of success, p equals 0.25. And x here is exactly 3. So x equals 3. And again, notice we get the same answer. Okay, so you either have to show the actual equation work or you're showing work for calculator is you can say calc, binomial PDF, parenthesis, everything the calculator asks for. N equals 5, p equals 0.25, x equals 3. And that gives us a probability of about 8.8%. So let's look at another example. Should the parents be surprised if more than 3 of their children have type O? Well, more than 3 would not be a binomial PDF. That would be a binomial CDF. Again, here on the left side, more than 3 equates to I have 4 children or 5 children with type O. So again, if you want to use the equation, this would be the long format of adding those two together. But why not let the calculator do the work for us? So we're finding the probability that x is greater than 3. Greater than or less than is going to be binomial CDF. And I can show my work on the calculator by writing calc, binomial CDF, n equals 5, p equals 0.25. Here, because I want greater than 3, my lower bound, I can't have a half a child, so lower bound is 4, and upper bound is 5. And notice we'll get the same answer, probability of 0.0156, which is about 1.56%. So notice we haven't answered the question. It says, should you be surprised if more than 3? Well, my probability is about 1.6%. The answer would be yes, because there's only about a 1.5 or 1.6% chance the parent should be surprised if more than 5. or if more than 3 have typo. So always after you find your answer, reread the question. Make sure that you're actually fully answering the question, okay? Sometimes, a lot of times in statistics, it's not just about your number answer. You need to relate it to the problem, okay? So this is asking for a yes or no answer. Okay, so important part is yes, you can use a calculator. You have to show this step as you're showing work for calc. Again, AP test, no work, no credit. So let's look at mean and standard deviation. We describe the probability distribution of a binomial random variable just like any other distribution by looking at the shape, the center, and spread. And consider the probability distribution as, again, X, the number of children with type O in a family with 5. And it gives us this probability of each one here. So what do we notice about the shape? Again, the shape is skewed right. It is more likely to have 0, 1, or 2 children with type O than a larger value. Notice the center. The median number of children with type O is 1. And again, you can calculate the expected value exactly of that. You can find the mean. Again, median, you can just look at the bar graph or the histogram. Mean, you can calculate expected value, X times the probability, add them all up. We'll get about 1.25. If we look at the spread, we can calculate the variance using our variance formula, again, on AP formula sheet. We'll get a variance of 0.9375, and again, we can find standard deviation by taking the square root of that, 0.968. So on average, again, standard deviation means the average deviation from the mean is 0.968. So notice that the mean equals 1.25 can be found another way. Since each child has a 0.25 chance of inheriting type O, we'd expect 1/4 of the 5 children to have this split type. That is, the mean of X, mu of X equals 5 times 0.25, which equals 1.25. This method can be used to find the mean of any binomial random variable with parameters and NP. And notice we have 2 formulas dealing with binomial random variables. Again, these only work for binomial when I have only 2 options, success, failure. Our mu sub X equals NP, number times probability, very similar to expected value. And standard deviation of X, notice is different formula, big square root, N number of trials times P, probability of success, times 1 minus P, which basically means probability of failure. And again, cannot stress enough, these only work for binomial distributions. Therefore, your bends needs to be checked in order to utilize them. And what I often say is when you look at a problem, if you're unsure about what standard deviation formula to use, look to see what knowns you have. Okay, other standard deviation problems typically have extra variables in there. Mr. Bullard, so let's look at an example. Mr. Bullard's 21 AP statistics students did the activity on page 340. If we assume the students in the class cannot tell tap water from bottled water, then each has a 1/3 chance of correctly identifying the different type of water by guessing. So let X equal the number of students who correctly identify the cup containing the different type of water. Let's find the mean and the standard deviation of X. Since X is a binomial random variable with parameters, N equals 21 and P equals 1/3, we can use the formulas for the mean and standard deviation of a binomial random variable. So if we calculate our mean, mu sub X equals NP, our number of trial students is 21. Our probability that they can use formulas is 1/3. So 21 times a third is 7. So we expect about 1/3 of his 21 students, about 7, to guess correctly. And if we calculate standard deviation, again, number of trials, students 21, times 1/3, times success, 1 minus P, 2/3 equals 2.16 after square rooted. So if the activity were repeated many times with the same group of 21 who were just guessing, the number of correct identifications would differ from 7 by an average of 2.16. So So when taking an SRS of size n from a population, we can use the binomial distribution to model the count of successes in the sample as long as n is less than or equal to 1/10 of our population size. Again, you can't have a sample that is almost your population, otherwise certain parameters won't exist. We call that our 10% rule. So as n gets larger, something interesting happens to the shape of the binomial distribution. The figures below show histograms of binomial distributions for different values of n and p. So what do you notice as n gets larger? So if we take a look at these distributions, notice here I just have a sample size of 10. Here I have a sample size of 20. Here I have a sample size of 50. What do we notice? Always our rule of large number says, okay, as I get more and more, as my sample size increases, I should be getting closer and closer to a normal distribution. So suppose that X has the binomial distribution with n trials and success probability of P. When n is large, the distribution of X is approximately normal with the given mean, mu sub X and sigma X. As a rule of thumb, we will use the normal approximation when n is so large that np is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. That is, the expected number of successes and failures are both at least 10. So you have to check this condition in order to use these two formulas. So let's look at another example. Sample surveys show that fewer people enjoy shopping than in the past. A survey asked a nationwide random sample of 2,500 adults if they agreed or disagreed that I like buying new clothes, but shopping is often frustrating and time-consuming. Suppose that exactly 60% of all adult U.S. residents would say agree if asked the same question. So let X equal the number in this sample who agree. Estimate the probability that 1,520 or more of the sample agree. So we'll verify that X is approximately a binomial random variable, so we gotta check the bins. So B means we need something called a success, something called a failure. So success is going to be yes, that we agree. Failure is going to be that we don't agree. Is it independent? Because the population of US adults is greater than 25,000, it's reasonable to assume the sampling without replacement condition is met. So yes, independent. Do we have a defined number of trials? Yes, it says out of 2,500 people. And S, probability of success, it says that exactly 60%, so P equals 0.6. So we also need to check the conditions for a normal approximation. So we need to check the 10% rule. Since NP, N is total number of 2,500 adults, times our 60% times 0.6, that equals 1,500. Yes, that is for sure greater than 10, check. And n times 1 minus p, so 2,500 times 0.4 equals 1,000. Yes, greater than or equal to 10. Check. Yes, you have to actually write that step down in order to proceed with your binomial calculations. So we are finding, calculate the probability that p of x is greater than or equal to 1520 using a normal approximation. So mu equals NP, so N is 2,500 times 0.6, so that gives us an average of 1,500. Sigma NP 1 minus P will give us, after square root, an average deviation from the mean of 24.49. Okay, so if we're looking for probability that X is greater than or equal to, and we know that this is a normal distribution, that means that we can find a z-score and use our z-table. So if you find the z-score, X minus the mean, so 1520, minus the mean that we just calculated, 1,500, divided by our standard deviation, 24.49, we get a z-score of 0.82. Again, you can pull up your z-table and look inside the table for a z-score of 0.82. So if you want to write it down in math talk, the probability that X is greater than or equal to 1520 equals the probability that Z score is greater than 0.82. Because we're looking for greater, that is the 1 minus inside the table. If you look inside the table, 0.79 would be the probability left. So we're looking right, 1 minus 0.7939 will get us a final probability of 0.2061. Or we could say about 20.61% of people have a chance of having a probability of 1,520 or more of the sample agree. Okay, so that concludes binomial notes. Key thing is that if you're calculating a binomial probability, calculation, it's fine to use a calculator, but you must show the calc steps.